Hello everyone. In this lecture we are going to discuss about graph representation. So previously we have already seen about graph and tree and why graph data structure is needed. All these things we had seen, right? Now we already knew that graph is just a consist of vertices and edges, right? So you can see the example. It is all about this round is vertexes, right? And this is a connection, that is edges. So if graph consists of vertices and edges, how can you represent this particular graphical representation inside a memory? That is a question. How can you represent it? Right. Now see, this graphical representation, it is for human being. It is for human being so that we can understand. But computer doesn't you can't directly store this graph inside a memory directly. Right? This is not possible. You need some representation so that you can store inside a memory. Right? So you can clearly see I written here. Now a computer must store this graph in a memory, right? So how it is possible, that we will see. See, our memory understand array, list, numbers, not drawings. Okay, drawing will not understand by memory, right? So we need some representation so that we can store inside a memory. And that representation, that method which we will use to store this entire graphical representation inside a memory, that method is called graph representation, right? Now there are commonly two types of methods. One is adjacency matrix and another is adjacency list. Okay, so it's like you can say that there are two different ways to store the same data. For example, this is a graph, right? To store them, this graph also represents a data, right? Entirely. So to store them, we have two different methods. That is matrix and list, using a adjacency matrix and adjacency list. So we can save the same data using a two different methods. Right, so this is what a graph representation is. Now we will see one by one that what is adjacency matrix and what is adjacency list. Okay, now we will see about adjacency matrix. That is our first method. So this is the example we have taken already. So we know in mathematics, for example, we have any matrix, right? If we have any matrix of any order, okay, so we can of any order, I don't know, n into n matrix, we can directly represent using a 2D array, right? So this part we know, right? If you have a matrix, if you want to represent it, you can make use of, if you want to store it, you can use a 2D array to represent this n into n matrix, right? Now what does this particular technique says this? Oh, okay, you can clearly see there is a connection. For example, if you see this example, from A to B there is a connection, right? From A to D there is a connection. That means A is connected to B and B is also connected to A. A is connected to D and D is connected to A. Now this is correlation, this is a connection. Now this connection can be established, this connection can be shown, okay, using this matrix representation. Okay, so it using a matrix representation, you can clearly see is there is a connection between two vertices. See, for example, from A to B there is a connection. I can clearly show that connection in the matrix also. I will show you how it is possible. Okay, so that is possible using a matrix representation, right? So I will take one example and I will show you how to represent this entire graph using a matrix representation, using a matrix. Okay, and it will show all the connection between all the vertices also. So I will show, we will see this example, then you will understand this theory well, right? Okay, now I try to represent this entire graph using a matrix. Okay, let's see how it is possible even. So what I will do is I will draw one graph. I will draw one matrix. Okay, I will take one matrix, right? Now what would be the order of this matrix? How can you say? So you can clearly see how many number of vertices are there. 1, 2, 3, 4. So the order of matrix will be 4 by 4. Okay, that means 4 rows and 4 columns, right? So this is how we represent the matrix. Now what would be the rows here? Okay, what element should be put in the rows and what element should be put in the column? How can you define? So it's simple. It is written number of rows. So wherever there is a rows, you directly put vertices, right? So here also at the row part I will put vertices only. Okay, so here I will put A, B, C and D. Fine. And in column part, what should I do? In column part, what element should be there? So here also, in column also you have to put the same vertices. So number of rows and number of columns is equal to number of vertices only. So in the row part also you have to put the vertices, and in the column part also you put the vertices only. So I am going to put the same thing. Here A, then B, and C and D. Fine. Now there is one simple rule here. See, whenever there is an edge exists between any two nodes, then you just put 1, okay, inside the matrix. And when there is no edge between any two nodes, then you just put 0. This is a simple rule you have to follow while constructing this entire matrix. Okay, so now let's see. For example, from A to, now start from A. From A to A. Start from row and column. So this is A to A, right? From A to A. From A to A. A to A, is there any edge? No. See, there is no edge, because A to A there is no edge. See, this is a simple graph. You can't have a loop like this. Okay, if there is a loop, then you can consider that there is some edge from A to A. So there is no self loop, so you can't consider anything between A to A. Okay, and moreover this is simple graph, so there would be no self loop also, right? So A to A there is no edge, so you can directly put 0 here, right? Now A to B, is there any connection? A to B, yes, so you put 1 there, right? Now A to C, is there any connection? A to C, no, so you put 0 here. A to D, is there any connection? Yes, you put 1 here, right? Now come to B part, right? Now B to A, is there any connection? B to A, B to A, yes, there is a connection, so put 1 there. B to B, no self loop is possible, right? So put 0 here. Okay. Now B to C, is there any connection? Yes, so put 1 here, right? And B to D, okay, B to D there is no connection, right? So directly put 0 here. Okay, can you observe how I am creating the matrix, right? Now come to C. Now look at C to A. C to A, is there any connection? C to A, no, there is no connection, so put 0 here. C to B, yes, C to B there is a connection, so put 1 here. C to D, C to C, no, C to C is self flow, there is no self flow, so 0. C to D, yes, there is a connection. Now come to D. Okay, now from D to A, is there any connection? Yes, so put 1 here. D to B, is there any connection? No, so put 0 here. D to C, there is a connection? Yes, 1. And D to A, is there is a connection? Yes, put 1 here. So this is how we complete our matrix. Now this matrix will clearly indicate the connection between two vertices. This is what we wanted, right? From A to A, if there is if there is a connection, you can directly see 0 and you can say no, there is no connection. So using this matrix information, you can again recreate the graph. Are you getting it in a graphical way? Okay, so computer, when you store this graph inside a computer, you will store in this format. Okay, and using this graph, you can again regenerate this particular graphical graph, this graphical representation, right? Is it possible? Yeah, it's definitely possible. You can directly construct it. You want to see whether I can do it? Okay, for example, this is the data given. Can I again recreate this graph or not, this particular graph? Let's see. It is possible. I want to show that demo. Okay, so we looking at this row and column, we understood there are 4 vertices, so I will directly put A, okay, B, okay, C and D, right? Now you just have to mention if there is a connection. Now A to A, is there any connection? No, we will not create any edge. A to B, is there any connection? Yes, 0 is 1. So that means there is a connection. So I will directly put a line. From A to C, is there is a connection? No, I will not put any edge. A to D, is there is connection? Yes, then I will put an edge between A to D. Right? So you can clearly see, I can recreate those. Now B to A, is there any connection? Yes, B to A, there is a connection. So the edge is already there. So you don't have to put one more edge. Okay, because it's an undirected graph. And B to B, there is no connection. So okay, 0. B to C, is there is any edge? Yes, 1. There is an edge. So you just put an edge between B to C. B to D, is there is an edge? No. So don't put any edge. Now come to C. C to A, there is an edge? No. 0. C to B. C to B, yes. There is already a connection. So you don't have to put again. Right. Now C to C. No. C to D. Yes. C to D, there is an edge. So you can see, you can directly create it like this. Right. Fine. Now coming to D to D. Now D to A, is there is a connection? Yeah, already there. D to 0, no. D to C, yes. D to D, no. So you can see I had recreated the entire graph again using this adjacency matrix. Right. So this is possible. So in simple word, adjacency matrix is nothing but a 2D array that shows the connection. Fine. Okay, we will see the next technique, which is called adjacency list. Okay, so in this what we are going to do is, instead of table, we are going to store a neighbors of each vertex. Okay, we are not going to use a matrix now. Right, so the name is adjacency list. Okay, so there is something called list, and list itself has to be stored somewhere, right? And for that we need something called array or linked list. In case in this method we are going to use both, right? So it is also called a two-level storage, right? I don't think you will understand like this, but remember in a C programming we have one concept called array of pointers, right? So that same concept we are going to make use of here in adjacency list. Okay, in that there is one array, right? And inside this array there is some address, right? And this address will point to some list, and that list is nothing but a linked list. Okay, if you do this thing, then it is nothing but adjacency list. Every cell will contain some address to a linked list. Okay, so if you try to maintain this is nothing but linked list, right? So if you try to maintain this, then this is nothing called array of pointer or array of linked list we can call, right? So we will see that part. Now there is one terminology we have seen, that we store neighbors of each vertex. See, neighbor is nothing. It is like, for example, A, right? This is A. A is a neighbor of B, right? Both are connected, right? And B is neighbor of A. That is the meaning. A is a neighbor of D and D is a neighbor of B, right? Or another way to say is A is connected to B and B is connected to A. A is connected to D, A is connected to D is connected to A, right? Or one more way to say is A is related to B and B is also related to A. So there are different terminologies. So while explaining also I might use different terminology. So please try to understand. Okay, so like I shown you an example. So for storing a vertices, I am going to make use of array, and to store a neighbors, that means which vertices are connected to that particular vertices. For that I am going to maintain a linked list. Okay, I am going to make use of singly linked list. Okay, fine. So with example you will understand better. Okay, so we will see the same example. Okay, this example, and we will try to represent using an adjacency list. Okay, so for that I told you, to represent a vertices we need an array. So I had taken one array, right? This is nothing but my array, right? Now inside the array, how many number of cells should be there? So you look at the vertices. How many number of vertices are there? 4. 1, 2, 3, 4, right? So we should have 4 cell. Okay, so I will draw 4 cell here. So one is here, 2, 3, right? And name that cell like A, B, C, D, the name of a vertices, right? So this is my array, right? This is my array, remember. Okay, now according to array of pointer concept, what would be there inside this array? Inside the cell of this array, it contained a address of some list. Okay, and in this case it would be a linked list. Okay, and this linked list will store what? Store the neighbors of each vertex, right? So let's see one example. So here A is related to whom? A is connected, or who is the neighbor of A? B, right? Means A is connected to B. So how can I represent that? Using a adjacency list, using a linked list. So what I will do is I will establish one linked list. Okay, there would be one pointer and I will establish one linked list here, right? This is a singly linked list, and inside this singly linked list I will store B, right? So what does it mean? That A is connected to B and B is also connected to A, right? So this is a neighbor because B is a neighbor of A. Now A is also connected to D and D is also connected to A. So how can I represent? I will create one more linked list like this. That is of D, right? And this is a singly linked list. I am representing is using singly linked list, right? Now what does it mean? That A is connected to D and D is also connected to E, or A is a neighbor of D and D is a neighbor of A. Okay, so this connection is established here. This both the connection between A and D and A and B is established using a adjacency list. So this is why what we call adjacency list. And is there any further connection for A or further neighbor for A? So for A, B and D is the neighbor, right? Any other neighbor? No. So we know this is the last, so you can directly put null here, right? This is the last node, therefore put the null here, right? Now what is next? Pick the next node, pick B, right? Who is the neighbor for B? A and C. So you establish a connection here. So design a linked list here, right? So do you point to right? Right? So for B, who is the neighbor? A and C. So A and C, and this part is null, right? Now for C, who is the neighbor? B and D. Yeah, establish a connection. So whoever the neighbor is, you just have to establish a linked list, singly linked list. That's it. So C to B, okay, is a neighbor, and C to D, D is a neighbor of, so B is a neighbor of C and D is also a neighbor of E, and there is no further neighbor, so you put a null there. Okay, now what about D? For D, A and C is the neighbor. There are two neighbors, right? So we'll draw two singly linked list. Okay, so who is the neighbor of D? C. And who is the neighbor of D? Again A, right? And these both are neighbors, so you can directly put a null here, right? No further neighbors are there. That's why I'm putting a null in the way at the end, right? So this is how we represent a adjacency list. Can you see? So we are coming to that point. For vertices, I had maintained a array. Okay, for neighbors, I had maintained a singly linked list, right? Can you see? So you can clearly see. So using this adjacency list also, I can again recreate this graph. You can do it. Okay, I will show that part also. Using I'd shown now for matrix also, using a direct matrix representation, you can again create that graphical representation. So yes, you can go a reverse engineering. Okay, so using a adjacency list, I can again recreate this graph also, right? So this is how the adjacency list works, right? Okay, now we will try to recreate the graph using this adjacency list. Okay, so I will show you that part, that reverse engineering. Okay, so let's see whether it is possible or not. So again, I know that there are 4 vertices, so I will draw 4 vertices: A, B, D and C. Okay, see this vertex, this particular graph, it's not that always when you try to recreate, it will look like this only. Okay, it may be D is here, C is here. Okay, it may happen. Okay, D is here, C is here, or A is here, B is here. Okay, it may happen. This interchange positioning of this node may happen. This is because I already knew that this is how the graph look like. Okay, so it's not always this positioning will be there. I already knew, that's why I'm drawing it, so that I can explain it in a simple way. Right, now let's see. From A to B there is a connection, right? So from A, you can clearly see from A to B there is a connection, from A to D there is a connection. So I will directly represent here. From A to B there is a connection, from A to D there is a connection. That's it. Now I will go to B. From B to A there is a connection, and from B to C there is a connection. Right? So from B to A, already connection is there. From B to C, yeah, I will put one connection here. Right? Now here come to C vertices. From C to B there is a connection, and from C to D there is a connection. So I will try to establish from C to B. Okay, there is already a connection, you don't have to put one more edge. C to D there is a connection, so put one edge. Right? From D to C there is one connection, from D to A there is one connection, from D to C, okay, connection is already there. D to A, connection is already. So okay, I recreated the graph using an adjacency list now. So it's working fine, right? So this is how the adjacency list is represented, right? So we see both the representation, okay, graph representation, that is adjacency matrix and adjacency list. Okay, it's very important. Okay, please note it down.